Okay, so we're now going to start, quite frankly, the last topic in this course here, but we will spend some time, we'll have several videos talking about this, which are frequency selective circuits. Actually, this is my favorite part of the course because I think it's pretty easy to see the application of frequency selective circuits, and in parentheses, the shorthand of what we really are looking at are filters. And then before we get started here, I just want to emphasize filters are used everywhere. And underline everywhere. I mean, you pretty much can't look at a circuit without there being some kind of filter there. And now, there's several things we can use filters for. One is to filter out, for instance, I'll say noise. So if there's noise in the signal, you can filter out the noise. And there's lots of different types of noise here. I mean, there's what's called white noise or Gaussian noise, and that's the kind of static-y thing that you're used to hearing. That has to do with like just atmospheric things, like radio signals passing through the air are going to pick up disturbances from the atmosphere because we've got electromagnetic fields all over the place. So that's what we consider white noise, and so we filter out the noise. Another is we'll put filters on power supplies. And you might say, well, why would I put a filter on a power supply? Well, a power supply isn't necessarily constant voltage, depending on what kind of power supply it is. If it's a battery, it's pretty flat. But if you're talking about some of the power supplies, including some of the ones that are on our workbenches, if you look at the voltage here and you really zoom in on the graph, the voltage, and it's a little bit more even than this, but this might be, for instance, 10 volts, but we have what's called ripple voltage. And actually, let me redraw that. I'm going to exaggerate it, but let me redraw it to make it a little bit more precise. And it actually is probably a sine wave as opposed to a triangle wave, but the idea is that it's a ripple voltage here, so it's not actually staying at 10 volts. And sometimes, depending on your circuit, it's critical that you maintain the 10 volts as opposed to fluctuate up, and it might only be fluctuating up between 10.1 and 9.9, or even smaller than that. And so it might be okay, the ripple voltage might be okay, but it might not be. And so one way to take care of this is you add filters to the power supply. And then kind of more obvious application here is dealing with sound. And I'll call this just an equalizer. So we'll just even do the simple example. If you adjust treble and bass in your car, you are adjusting filters. Now, when I say adjusting filters, we're not actually adjusting the frequency of the filters, we're adjusting the gain of the filters, which is something we'll talk about in a little bit more detail. So basically what we're saying is that the bass might be set for, let's just say, 500 hertz for the bass channel, and then everything above that is considered treble. So you'd have a filter that filters out the bass, so you can amplify just the bass, or you'll have a filter that filters out the treble, so you can amplify just the treble. And then you'd combine the signal again to put to your speakers. Or if you have tweeters and a subwoofer, you'd put the high frequency to the tweeters and you put the low frequency to the subwoofers. So there's also a lot of other, so not just with equalization, we can even put it here with sound music going to speakers. As if you've ever seen a speaker with like a box speaker that has more than one speaker in it, there's going to be a bigger one, that's the subwoofer that the low frequencies go, and there's going to be a really small one. There might even be a middle-sized one for mid-range frequencies, but if you only have two, one's going to be for the bass and one's going to be for the treble. And that's just so that, again, how sound can be delivered. It makes it so that you have the speakers that can deliver the largest range of frequencies for us to hear. Because if you just do a single speaker, you're not going to get necessarily all the frequencies adequately projected from that speaker. Alright, so the rest of what we're going to do in this video here is more just kind of some preliminaries, some definitions. Some of you might know this, but this is something that, at this point, if you've never been exposed to electrical engineering or circuits or filters, we need to get some of this definition out of the way here. So let's first look at the first two things here. Is we got a pass band and then a stop band. And the pass band is literally the frequencies that get passed by the filter. And the stop bands are the frequencies stopped. I like to think of it as rejected by the filter. So those are two important concepts, pretty easy to do. We have a frequency response graph. Because what we're going to be interested in how this filter behaves with respect to frequency. And we can also, it's also going to be important on how it behaves with respect to time, but the first thing in introduction to filters that we want to know, how does this respond with frequency. And so there is something that we call a Bode plot. And really, a Bode plot, some people think it's just one graph. Technically, I like to think of it as two graphs here. And the two graphs that we will see here are the following here. So we'd have the magnitude of H at j omega, and then we have the phase angle of j omega. And what we mean by phase angle is there is going to be some phase that, and actually, instead of putting that line there, I'm just going to leave that line out. There's going to be some phase angle that we have here with filters. Now, common just kind of one to start with here is if I have 0 dB and actually I will go ahead and put in the axis down here. And then we would call this omega c. And then for this kind of filter, this is again the magnitude, and here this is the phase. And the phase for this one is going to go start at 0 degrees and go down. And then what we'd say is here it's going to go down to some theta at j omega c. So it starts at 0 degrees. Now, we're not going to talk a lot about the phase diagram in this course. This will come back up because phase diagrams are actually extremely important One thing they're important with is with sound, but also if you're wanting to talk about the stability of your filter, which is a concept that we talk about in the advanced filter design course, you need to look at your phase plots to make sure your filter's stable, because we want stable circuitry. And we'll define stability in more detail as well. Now this here, what I've drawn here, the other thing I want to point out here is that the frequency here is log scale. And so this is log scale as well. And so for instance, if we're doing log scale, this might be 10, 100, 1000, 10,000, so on and so on. So each tick mark that you put linearly here is actually an exponential gain, magnitude of 10. Now, the thing to remember that this is omega, so this is in radians per second. This is not hertz. If you plot this here, j omega, it's in radians per second. Now, if you divide by 2 pi, you get hertz. And depending on the application and what you're really focusing on, sometimes we leave it as radians per second and sometimes we leave it at hertz. When we do design, we often will be looking at hertz because that's usually a lot of times where the specifications come in. They come in hertz, but we can convert hertz to radians per second pretty easily as well. And of course the same here would be true, as a side note here, the same would be true for the phase. This is 10 hertz, this is 100 hertz, not hertz, I just did the same thing here. These are radians per second. Now I want to emphasize here something. This is an ideal filter. Because what we can see here is 0 dB corresponds to a gain of 1. So that means V out is equal to V in. So a gain of 1 just means that the output voltage is equal to the input voltage. And then abruptly we drop down to essentially negative infinity, which means that none of the frequencies above 100 rads per second are passed through. So these are absolutely an ideal filter. And this here, just to go back to our definitions, this would be my pass band, and this would be my stop band. And now, with this diagram here, we're going to go ahead and start naming these types of filters, and the names kind of go along with just what is the signal being passed. And so the name here would be, well, I'm passing low frequencies through and I'm stopping high frequencies. So this would be considered a low pass filter. Now before we move on, I just want to emphasize it's not low pass because it's cutting off at 100 radians per second. It's low pass because it's letting low frequencies go through. And the reason I want to point out that is I could relabel these diagrams here and just say, for instance, that this was 1 gigarad per second, and I could have that be my low pass filter where I pass all frequencies up to 1 gigarad per second, and then I stop frequencies higher than that. That would still be a low pass filter. It would just be having the cutoff frequency be much higher. So low pass does not mean you're passing, like the cutoff frequency has to be low. It just means anything less than the cutoff frequency gets passed, anything above the cutoff frequency gets stopped. That's what you want to remember for low pass filters. And we're going to wrap this video out here with some of the other some of the other filters, and you can probably guess at what some of these other filters are going to be here. If we have a low pass, it kind of makes sense that we have a high pass filter, And so if we try and draw what a high pass filter would look like, and I'm going to draw the ideal cases in all these situations. You know, the next one that you might guess is that we'd have an omega C here, and instead of stopping the low frequencies, instead of letting through the low frequencies, we let through the high frequencies. And the phase plot for this is we start with some, and we go down to 0. And so this would be theta at j omega C. And again, this is my cutoff frequency, omega C. This is my stop band. Let me pause the video. Okay, so your screen probably just jumped here a second. My program crashed, and I actually lost quite a bit of information, but it's not a big deal because I just used this as a way to write my notes. My notes are, this isn't my master copy of my notes. But we were here, and we were writing down here that this was the stop band, and this was the pass band. And then we had our phase diagram down here, and again, these are in log scale, but we can guess what this one would be called. This would be called a high pass filter. And now again, I want to emphasize that it's not because omega C is a large frequency. Omega C might be 1,000 radians per second, and so what that means is that any frequency above 1,000 radians per second gets passed, anything below it gets stopped. So just because it says high pass does not mean that omega C is a large frequency. It means that we're letting through any frequencies above omega C. Now, there's two other common types of filters here. There's lots of other filters, by the way. This is not by any means a true encompassing of all the filter types. Obviously, if we have a whole course devoted to just a 3-credit-hour course for a whole semester devoted to filter design, there's a lot more to do with filters than what we're introducing here. But another filter here that we have will have two cutoffs, omega C1, omega C2, still being in the and then this is 0 dB, and this is stop. This is pass, and this is stop. And then the phase diagram for this looks like the following. Whoops, can't draw a straight line here. That's still not that straight, but you get the idea. And this would be 0 degrees. And as you can kind of guess what this would be called a bandpass filter. And finally, there's one more filter. And, well, quick application of a bandpass filter. Anytime you tune your radio to a particular station, you're using a bandpass filter because you're letting in, like for instance, if you're tuning to 96.3 FM, I don't even know if that's a station, but let's just say you're tuning into 96.3, which, by the way, that's in megahertz, so 96.3 megahertz. You're not just looking at 96.3 megahertz. Roughly speaking, and now this isn't precise, but roughly speaking, you're looking at frequencies you're letting frequencies from 96.2 megahertz up to 96.4 megahertz in, because that's what contains all the information for the audio signal. Now that's just a rough approximation, that's not precise, but obviously there's a bandpass filter that we have to do because we're letting in a particular band of frequencies. Alright, now the other filter that we do have and that we can look at, and it's kind of the opposite of a bandpass, where we have the filter that looks like this. We pass these low frequencies, we stop these middle frequencies and we pass the high frequencies. And the phase diagram for this one is a little unusual here. So, and that's just because of the fact that we have these quote discontinuities here. Real filter wouldn't look that. I'll show you in a second what a real filter would look like. So, but the phase diagram would look something like this, where this is omega C1, then omega C2, look something like that. And these wouldn't necessarily be the same slope, by the way. And they're not the same slope here. And then this is called a band reject filter. Now, one quick last thing to finish this video, and I've been managing to make these videos longer and longer, and I really like to keep them to no longer than 15 minutes, and then here I'm talking more, making it even longer. But I want to show you quickly what a true band reject filter would look something like. So let's say this is 0 dB here. Omega C1, I'm sorry, this would be omega C2. This would be omega C1. And this might be, for instance, now, as a side note, the decibels are usually in linear units here. This might be, for instance, minus 70 decibels. So it's not that they, completely go away, they essentially go away. And so we'll talk more about that when we talk about decibels in the next video.